In this video, I'll go over the quiz questions on liquids and solids. Question 1. Liquids have a definite volume, but not a definite shape. Gases do not have a definite volume or shape. So, volume, shape, gases. The density of dry ice at negative 80 degrees Celsius is 1.5 gram per milliliter. The question is about the molar volume. So if we have 1 mole CO2 solid, it weighs 44 grams, carbon 12, oxygen 16 times 2, so 44 grams. And 44 grams divided by the density will give us the volume per mole. That's 29 milliliters. We don't see 29 milliliters per mole, so we find this answer here. This is exactly 29 milliliters because 1 cubic meter is 1 million millimeters. 1 cubic meter is 1,000 liters. So we're going to choose this one. How about this? This one is off by a factor of 1,000. The answer is 29 milliliters per mole, not 29 liters per mole. The density of dry ice at negative 80 degrees Celsius is 1.5 gram per milliliter. What's the average space each CO2 molecule occupies in dry ice? So over here, if 1 mole CO2 molecules occupy this much space, and then we just need to use this number divided by the Avogadro constant, 6 times 10 to the power of negative 23. So the result is, again, this is 29 times 10 to the power of negative 6 divided by 6 times 10 to the power of 23. So it should be 4.8 times 10 to the power of negative 29 cubic meters. So this is correct. And 1 cubic meter is 1 million centimeters. So this is correct. And also 1 liter is, well, these two numbers are the same. And 1 cubic centimeter is 1 milliliter, so this is correct. And now 1 liter is 1,000 milliliters, so this number is correct with this corresponding unit. The average distance between neighboring CO2 molecules. So if we imagine each CO2 molecule occupies a cube, the edge length of the cube is the cubic root of this number. So we just need to take the cubic root of this number. So it's 48 times 10 to the power of negative 30. And then what's the cubic root of 48? Well, it's between 3 and 4. All right? Because 48 is between 27 and 64. 27 is 3 to the power of 3. 64 is 4 to the power of 3. So we're going to get a number between 3 and 4 times 10 to the power of negative 10. Well, it's just this, 3.6 times 10 to the power of negative 10. And 1 nanometer is 10 to the power of negative 9 meters, so this is also a correct answer. And 1 nanometer is 10 angstroms, so this is a correct answer as well. Question 5. The molar volume of CO2 gas at this temperature and 1 bar pressure is roughly how many times greater than the molar volume of dry ice? We just need to use PV equals nRT to get molar volume of CO2 gas. At this temperature and 1 bar pressure, again, you use PV equals nRT. So V over N is RT over P. So you just need to do RT over P. Make sure you pay attention to the units. If you do that, I think the result is going to be roughly 30 liters or 0.03 cubic meter. All right, and then let's see how many times greater than the molar volume of dry ice. So the molar volume of dry ice is 29 milliliters per mole. The molar volume of this gas is roughly 29 liters per mole. So 29 liters over 29 milliliters, so I'm going to say maybe 1,000 right here. So you just need to estimate the molar volume of the gas, because if you look at this for different options, 100, 1000, 10,000, 100,000, so they differ by at least a factor of 10. So you just need to estimate. It's going to be 1,000 times larger. And if the volume is 1,000 times larger, that's 3 dimensions. That's 10 to the power of 3. So in each dimension, we're going to, later we're going to see the average distance between CO2 molecules is about 10 times larger than the CO2 in the solid state. But let's look at this density here. If the molar volume is 1,000 times larger, then of course the density is going to be, well, 1 over 1,000 times the density of dry ice. So we're going to pick this one, 1 over 1,000. Now let's talk about the average distance. That's in one dimension. So if we have a bunch of molecules confined in a container of, let's say, 1 milliliter versus 1 cubic meter, the volume differ by a factor of 1,000,000. What about the difference between their edge length? Well, they only differ by 100. Why? Because again, the volume of a cube is the edge length to the power of 3. Now let's look at this question. The average distance between CO2 molecule in the gas phase versus that in the solid phase. Again, we're just thinking about the molar volume. It's roughly 29 liters versus 29 milliliters. So they differ by a factor of 1,000 in volume. And volume is the edge length to the power of 3. So the edge length of the gas phase versus the solid phase has a 10 to 1 ratio. So that's why we're going to choose a 10 to 1 ratio here. All right. Submit quiz. All right, 5 out of 5. We're done with this one. Let's look at this one. Vegetable oil has a higher boiling point than water because vegetable oils usually have a boiling point of 200 degrees Celsius or even 300 degrees Celsius versus the boiling point of water, which is roughly 100 degrees Celsius under 1 atm pressure. Well, vegetable oil, it's mostly hydrocarbons, with some functional group. And usually vegetable oil has a long carbon chain. Therefore, vegetable oil has a much stronger dispersion than water. Water molecules actually have a larger dipole moment. Therefore, actually water has stronger hydrogen bonding than vegetable oil. So this one is just the opposite of the fact. Choose all types of intermolecular forces introduced in the video, so you have to watch the video. But if you know the intermolecular forces, you know there's ion-ion, there's dipole, and induced dipole, between ion and induced dipole. So over here, if you place a sodium plus near a helium atom, you can actually induce a dipole moment in the helium atom. Dipole-dipole and hydrogen bonding. Hydrogen bonding is just one of the strongest dipole-dipole interaction. And between instantaneous dipole and induced dipole, maybe between 2 helium atoms, that's a good example. And dispersion. Dispersion, again, it's caused by instantaneous dipole moment. So all 1, 2, 3, 4, 5, 6, 7, all 7 answers are correct. Intermolecular forces are loosely interpreted as intermolecular energy in the textbook and in video. They are, however, a little bit different. Force is in Newton, energy is in Joule. So we're going to choose Newton and Joule. 1 Newton times 1 meter is a Joule. So Newton and Joule. And these two look similar, but pay attention here. Over here, this is meter, this is meter squared. Over here, this is meter squared, this is meter. So if we're looking at Newton, it's 1 kilogram times the unit of acceleration, so it's meter divided by second squared. What about Newton? This is Newton. What about Joule? This is Joule. Joule is 1 Newton times a meter. So Which of the following chemicals has the highest boiling point? 1, 2, 3, 4. Well, if you watched the video, you know the boiling point of water is 100. These two have much lower boiling point because in these two molecules, in these two gases or liquids, actually, in these two liquids, you can form only one hydrogen bond per molecule. In water, you can form 2 hydrogen bonds per water molecule. So again, each water actually can form 4 hydrogen bonds, but again, each hydrogen bond is formed between 2 water molecules. So 1 mole water forms 2 moles of hydrogen bonds. What about ethanol? Actually, ethanol has a greater dispersion than water because of the longer carbon chain here, but again, in ethanol, there's only 1 hydrogen bond per ethanol molecule. So actually, ethanol has a lower boiling point than water. You can also Google the boiling point of ethanol. I think it's roughly 79 degrees Celsius. Question 5. Which of the following chemicals has the highest boiling point? So first, rule out the noble gas atoms, and then compare this to, this one has a longer carbon chain, therefore greater dispersion, so over here. Which of the following chemicals has the lowest boiling point? Well, this time we're going to lower the boiling point. That means we're looking for the weakest ion-ion attraction. So when we're talking about weakest, so first we need to look for ionic compounds with the fewest charges, but also the longest distance. So first, let's rule out barium oxide and calcium oxide. Because in these two ionic compounds, both this positive ion and the negative ions have 2 charges, either +2 or -2. So that's very strong attraction. There are only 2 options left: sodium chloride versus cesium bromide. Okay, look at the ionic radius of cesium. It's much greater than sodium. The ionic radius of bromide is much greater than that of chloride. And they have the same +1 and negative charges. This one has a longer distance between the 2 charges, so I'm going to pick this one. Alright. Question 7. On average, the hydrogen bonding between 2 hydrogen fluoride molecules is stronger than the hydrogen bonding between 2 water molecules. However, the hydrogen bonding in 1 mole liquid water is greater than the hydrogen bonding in 1 mole liquid hydrogen fluoride. Why? Well, it's just because of the different numbers of hydrogen bonds. In water, you can form on average 2 hydrogen bonds per water molecule, and then in hydrogen fluoride, there's only 1. So we're going to pick this correct answer. On average, each water molecule forms 4 hydrogen bonds with their neighboring hydrogen molecules, but there are only 2 moles of hydrogen bonds in 1 mole ice. Well, again, each hydrogen bond is formed between 2 water molecules. So if you count 4 hydrogen bonds for every single water molecule, you double counted every single hydrogen bonds. Alright, so what I'm going to do is I'm going to click this. Each hydrogen bond is shared by 2 water molecules, and the same hydrogen bond should not be counted twice. If liquid A has a much higher boiling point than B, then very likely, okay, higher boiling point and much higher boiling point. That means the attraction between A and A is greater than the attraction between B and B. That's what we know. And if you have a stronger attraction between A and A, well, there's going to be greater surface tension. A is trying to minimize the surface area. And also, because of the attraction, you're going to observe higher viscosity, of course. Alright, of course, viscosity does depend on something else, like temperature and also the shape of the molecule, but, you know, assuming all other factors are the same, I'm going to click this. Let's see, 7 out of 7, so we move on here. Vegetable oil is less volatile than water. Okay, less volatile. Volatile means, well, easier to evaporate. It's more difficult to evaporate vegetable oil. You can do this experiment at home. Just get, you know, a drop of vegetable oil and a drop of water. somewhere and see, after a day or two, the water is going to disappear, the oil is going to be there. Vegetable oil has a higher boiling point than water, actually much higher. Vegetable oil is more viscous than water. You can kind of just pour vegetable oil and see if it's faster or slower than water. So less volatile, higher, and more viscous. Less, higher, and more. Less, higher, and more. The water vapor is this much, and this much at this three temperatures. And now you're going to use Excel spreadsheet to calculate the water vapor pressure at 80 degrees Celsius. So essentially what you need to do is this. You need to create a Excel spreadsheet, and you put these numbers in, but don't use those data directly. You need the logarithm of the pressure, and you need the reciprocal of the temperature in Kelvin. So you somehow need to convert this 0.01 to 273.16 Kelvin, and then take the reciprocal of this 273.16, and then you get the slope. After you get the slope, you have this enthalpy of vaporization for water. Why? The slope of LNP versus 1 over T has a slope of negative enthalpy of vaporization over R. So that's how you get that. And also, you can use that graph to do linear fitting or linear regression. You'll get a linear equation that tells you how the logarithm of the pressure depends on 1 over T. And then you just plug in 80 degrees Celsius in the temperature. But before you do that, make sure you convert 80 degrees Celsius to 753.15 Kelvin, and then you will get the correct logarithm of the pressure. So I think it's 0.46. You can also use Wolfram alpha as well, included in the lecture notes. All right, again, similar problems. You're going to use this Clausius-Clapeyron equation. You're given the pressure, you're given the temperature, but make sure that you convert the pressure to the logarithm of pressure. You convert temperature to Kelvin and then take the reciprocal of it. So that's very important. So basically, this liquid boils at 60 degrees Celsius against 1 bar pressure. It can actually boil at 40 degrees against 0.5 bar pressure. So you take the logarithm, you make the graph, or you can simply do a calculation. The logarithm of these two differ by ln2. ln2 is 0.0693. And then you take the reciprocal of these two numbers and take the difference. So this number is going to be 1 over 313. This number is going to be 1 over 333. You take the difference between these two, and it's going to be roughly 20 over 10 to the power 5. So it's going to be the reciprocal of 5,000-ish. All right, I'm just calculating this on the fly. So 5,000 times 0.7 times R, that will give you the enthalpy of vaporization for this liquid. All right, I think it's going to be roughly 30-something. Roughly. When water reaches equilibrium with its vapor, what will happen to the water vapor pressure? If we cover half of the surface with a parafilm used in a chemistry lab, or simply food wrap, either way, you will reduce the evaporation rate by 50%. You will reduce the condensation rate by 50%. So after you do that, the evaporation rate is still equal to the condensation rate. So there's going to be no net change. Therefore, no effect because both rates will be reduced by 50%. Similar question, but this time we're going to dilute water with another liquid. Well, that will definitely reduce the number of water molecules on the liquid surface. Let's say we do 1-to-1 mole ratio, all right? Let's say 1 mole water, 1 mole ethanol, we mix them, and then on the liquid surface, you're going to get 50% water molecules and 50% ethanol molecules. So what does that mean? That will reduce the evaporation rate of water by 50%. What about condensation rate? No change. Because for water vapor to condensate to the liquid surface, you still have the entire surface. So what does that mean? That means the condensation rate is going to be greater than the evaporation rate if you dilute water with ethanol. Well, and then that will reduce the number of water molecules in the gas phase. Water vapor pressure will decrease. Question 6. The vapor pressure of a liquid is higher at a higher temperature. Well, it's very simple. Temperature is a measure of the average kinetic energy. You should talk about that. There's going to be more energy, and water molecules can have more energy and then more likely to overcome the attraction from the surrounding water molecules. We call that hydrogen bonding. So between these two, you want to pay attention to this hydrogen bonding versus ion-ion attraction. Between water molecules, that's hydrogen bonding. Question 7. So, to design this question, I actually boiled tap water and tap water plus a lot of salt inside. So, a saline solution. And in the video, I think the boiling point of tap water is roughly 99 degrees Celsius, and the boiling point of the salt solution is 103 degrees Celsius. All right, let's look at this. The boiling point of tap water or pure water is roughly 99. If you really can get pure water and you do this experimental experiment more carefully with a very accurate thermometer, I think the boiling point is going to be 98.5-ish, 98.3, between 98.2 to 98.6, roughly that. Again, it's because we live in Ellensburg. The pressure is lower than 1 atm, therefore water boils more easily under a lower than 1 atm pressure. So, but anyway, in this question, it's 99. It's shown in the video. Watch this video again if you have not done so, and the salt water boils at 103 degrees Celsius. There are two correct answers. First, if you add anything in water, as long as that anything dissolves in water, you're going to have fewer water molecules on the surface. All right, that will reduce the evaporation rate. So that makes the vaporization of water more difficult. So you need to choose that answer. So it's going to reduce the evaporation here. And two, ions attract water molecules, and they may stabilize water molecule in the liquid phase. All right. So let's choose this answer. 7 out of 7. So we move on to the next one. The enthalpy of fusion of water is 6 kilojoule per mole. Enthalpy of freezing, okay, -6. -6 kilojoule per mole. That's it. Because freezing is just the opposite process of fusion. The enthalpy of sublimation is 51, and then the enthalpy of deposition, aka desublimation, just change the sign, -51 kilojoule per mole. That's it. Pay attention to the units. Make sure you use the correct units. All right, over here. So you are given the enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation. It turns out the enthalpy of fusion plus the enthalpy of vaporization is equal to the enthalpy of sublimation approximately. Why is that? Well, enthalpy is a state function. So if you want to calculate the change of the enthalpy from ice to gas, you can do it in a different way. You can go from ice to liquid water first. That's going to be 6. And then you go from liquid water to vapor. That's 45. And you can sum it up. That's 51. So really, you want to say enthalpy is a state function. And if you want to calculate the change of the enthalpy, you can actually design different processes. You can go from ice to vapor directly. You can go from ice to liquid and then to gas indirectly. You're going to get the same answer. So this is not purely in coincidence. There's a reason for that. Enthalpy is a state function. The transition from solid to gas, sublimation, gas to solid, deposition or desublimation, solid to liquid, fusion, liquid to solid, freezing. So what I'm going to do is sublimation, deposition, and fusion. Oh no, this one's wrong. Sublimation, deposition, fusion, freezing. Okay, this one is correct. The enthalpy of fusion is 6 kJ per mole. How much heat is required to melt 1 pound of ice? Okay, 1 pound, that's 453.6 grams. Roughly, you convert that to the number of moles first. Okay, you need to do that. And how many moles is that? You need to use 453 divided by 18. I think that's roughly 25-ish. And then 25 times this number, you're going to need 150 kilojoules. Okay, so 150 kilojoules. It's not this. It's not this. It's 15. We need 150. 150 divided by this number, we're going to get kilocalories. So 150 divided by 4, it's going to be 36-ish. So 36 kilocalories. And 36 kilocalories is this number. Okay, 36,000 calories. The enthalpy of sublimation is 51 kilojoule per mole at 0 degrees Celsius with 1 mole of water vapor deposit. So that's the opposite of sublimation. So we're going to have negative 51 times 0.1 mole. So that means when this deposit heat is going to be released. All right, and we have only 0.1 instead of 1 mole. Submit the quiz. Oh well, let's see. 5 out of 5. So we move on to the last quizzes. Calculate the amount of heat required to melt 1 gram of ice at 0 degrees Celsius, 1 atm pressure. So we got this number here, but this is per mole. 1 mole water is 18 grams. So we need to have this divided by 18. All right, 6,000 divided by 18. That's 330. So over here. Calculate the amount of heat required to evaporate 1 gram of liquid water. So we have the enthalpy of vaporization in kilojoule per mole. So what we need to do is, again, we need to have this number divided by 18 grams per mole. So 44 divided by 18, that's going to be 2 point something, maybe 2.4, 2.5 kilojoule. That's this one. All right. Calculate the amount of heat required to turn 1 gram of ice at negative 100 degrees Celsius to 1 gram. Oh, this is really complicated. So it's a complicated process, but again, because enthalpy is a state function, and because the change of enthalpy is equal to the amount of heat that flows into the system under constant pressure condition. So we're going to just look at this process. First, we need to increase the temperature of this ice from negative 100 degrees Celsius to 0 degrees Celsius. All right, how much heat do we need? So we need 100 and times this 2.1. All right, and then times 1 gram, right? 100 degrees Celsius times this one times 1 gram. It's just 210. It's only 210 joules. It's a small number. And then how much heat do we need to melt this? 330. I think we calculated this before. All right, so 210, 330. And then we are going to increase the temperature of the liquid from 0 degrees to 100 degrees. How much heat do we need? So 100 times this 4.2, we need 420. So we get 210, 420, and then we get 330. So it's almost 1,000 joules already. And then we're going to vaporize this water. That's a lot. So it's going to be, we're going to look at this number divided by 18 grams per mole because we have only 1 gram of water here. So this is 4 per mole. So this number divided by 18 roughly 2.5 kilojoule per gram. and then plus the previous 0.9 kilojoule or 1 kilojoule, so we got roughly 3.4 kilojoule already. And then we need to increase the temperature of this water vapor from 100 degrees Celsius to 200 degrees Celsius. So again, we need the specific heat here times the grams of water vapor times the temperature change, which is again 100. So we're gonna add 200 joules or 0.2 kilojoule again. So after adding up all those numbers, it seems this number is the closest. So I'm gonna pick this number, 3,000-ish joules. All right. Question 4. This time, this is actually easier. We're gonna just turn 1 gram of ice at negative 20 degrees Celsius to 1 gram of liquid at 20 degrees Celsius. So again, we just increase the temperature of ice from negative 100, negative 220 to 0, and then we melt it, and then we increase the water temperature by 20 degrees from 0 to 20. So that's what we're gonna do. From negative 20 to 0, the temperature change is 20, and we have 1 gram, so 20 times 1 gram times 2.1, that's going to be 42 joules, 42 joules. And then we're going to melt 1 gram of ice, 330. That's going to be 330. So this number divided by 18 grams. So this number is for 18 grams of water, but the question is concerning 1 gram. So this number divided by 18, it's going to be 330 joules. So 42 joules, 300. We got 370 already. And then we need to increase the water temperature. So 1 gram times 20 times 4.2. So that's going to be 84. So 400 something. Okay, 400 something over here. Question 5. All right, we're going to convert 1 gram of liquid water at 20 degrees Celsius to 1 gram of water at 120 degrees Celsius. How much heat is needed? So first, we're going to heat up this liquid water from 20 to 100. So that's a temperature change of 80 degrees. So 80 times 4.2 times 1 gram, that's about 340 joules. And then we're going to vaporize this. It's going to be, again, this number divided by 18 grams. Divided by 18 grams. So it's going to be roughly 2.4 kilojoule per gram. And then we need to increase the water vapor temperature from 100 to 120. That's a small number. It's going to be just 2 times the temperature change, which is 20 times 1 gram. So it's just 40 joules. You probably have realized that most of the heat is used to evaporate or vaporize this liquid water. It's 2,400 something. So the answer is going to be this. CO2 is 100 atm pressure. You do need to look at the phase diagram of CO2 in the lecture notes. So under really high pressure, CO2 can exist in the liquid phase, and under this condition, it's indeed a liquid. 10 atm, negative 70 degrees Celsius. Okay, I need to look at the phase diagram because I don't remember 10 atm, negative 70 degrees Celsius. So this is PT diagram. I really want to show you the lecture notes and PT diagram. This is CO2. All right, so the question is, this is CO2. Oh wait, this is still water. This is CO2. Negative 10 degrees Celsius. 70. Oh, that's liquid. So what about 100 degrees 100 atm and 0? Oh, that's also liquid. All right, get back to the quiz. 0 degree Celsius and 100 atm. 0 degrees Celsius and 100 atm, that's liquid. And then the next question is 10 atm, negative 70 degrees Celsius. I think it's still liquid. Yeah. 50 degrees, 200 atm, very high pressure. 50, 200. Somewhere here. That's supercritical fluid. So if the temperature is higher than the critical temperature and the pressure is higher than the critical pressure, you have a supercritical fluid. A supercritical fluid behaves like a liquid and a gas. Its density is roughly maybe 10% to 50% of the liquid. So it's the density of the supercritical fluid is much higher than gas. So in that sense, it looks like a liquid. But in some other senses, for example, a super critical fluid does not have a finite volume. You can actually change its volume more easily than a liquid, so it's more like a gas in that sense. So anyway, let's pick this supercritical fluid. Really high temperature, really high pressure. So this 50 degrees Celsius is fairly high for CO2. The solid, liquid, and gas phases of water can coexist under this temperature and this pressure. That's the triple point of water. So let's look at the phase diagram of water. So it's right here. There's a triple point, 0.06, 0.01 degrees Celsius. So that's correct. True. Water is in what phase? At 300 degrees and 220 atm. So this is very high pressure and temperature for water. 300 degrees Celsius, 220 atm. 220 atm, so it's somewhere here, and then the temperature is really high. But wait, it's kind of close. 300 degrees Celsius, 220 atm. 300, that's here, and 220, it's here. So I think it's still liquid phase. It's still a liquid phase. You need a higher temperature. You need a temperature higher than 374 degrees Celsius. All right, so it's still a liquid. All right, pure water at 0 degrees Celsius when the pressure changes. So we're going to focus on the pressure change. The temperature is 0 degrees Celsius. The pressure changes from 0.0001 atm to 200 atm. So we need the phase diagram of water from really, really low pressure. So maybe here, all the way up. So this line all the way up. First it's a vapor, and then it's ice, and then it's liquid. It's strange. If you are lowering the pressure of water from 0.0001 atm to 200 atm at 0 degrees Celsius, again a constant 0 degrees Celsius temperature, water is gonna turn from vapor to ice and then liquid when you are increasing the pressure. So ice, a gas to ice, gas to ice to liquid over here. Describe the phase change of water at 1 degree Celsius when the pressure changes from this low pressure to high pressure. So 1 degree Celsius, it's right here, okay, above 0.01. Okay, it's going to be from gas to liquid directly. It does not cross the solid phase. All right, so we're going to just say from gas to liquid. It is possible to compress liquid water to ice at proper temperatures, but it is impossible to compress liquid CO2 to dry ice. And this is interesting. This is, one of the most confusing problems regarding phase changes. So if you exert a really high pressure, you can convert a substance from a lower density state to a higher density state. Okay, from a lower density state to a higher density state. So if you compress water, you can convert it from ice to liquid. All right, and then if you try to compress CO2, yes, you can compress CO2 from liquid to solid. So both statements are the opposite of the fact. All right, we're gonna submit it. 7.5 out of 8. So I got something wrong. Here. I need to over here. CO2 is in what phase? At -7 0 degrees Celsius and 10 atm pressure. So negative 70 degrees Celsius and 10 atm pressure. CO2. Negative 70. Okay, negative 70 is here. And I forgot what the pressure is. 10 atm pressure. Negative 70, 10 atm. Okay. Negative 70, 10 atm. And obviously it's in the solid region. It's in the solid region. I selected liquid. I don't know why, but anyway, it should be solid. Again, this is how you look at the phase diagram. If you're told its temperature is negative 70, so find negative 70. And then 10 atm, you just go up, find this 10 atm right here. This is a solid phase. It's a solid phase. But if we maintain this 10 atm pressure and gradually increase the temperature under 10 atm pressure at this point, roughly negative 59 degrees Celsius, CO2, dry ice is going to melt. And then negative 50 degrees Celsius and 10 atm pressure, it's going to be a liquid. Sorry about that.